So welcome everyone. In the last video, I discussed about the Wittig Olefination, which is probably one of the most prominent and best method that is usually employed for the synthesis of alkene moiety. So in this video, I'm going to talk about yet another method which is called Peterson Olefination, which is usually employed for the synthesis of alkenes. And depending upon the conditions that we used, either acidic or basic, we end up getting either Z-olefine or E-olefine exclusively. This is because under both these conditions, the reaction follows either sil elimination or anti-elimination. Okay, so let's look at what this reaction is all about. So this is nothing but a silicon version of a Wittig Olefination. Since in the case of Wittig, what we use is phosphonium salt, so here we are using silane, SiMe3. Okay, here we are using silicons. Now this involves a reaction of either aldehyde or a ketone. So what you start up with is an aldehyde or a ketone, and then what you take is an alpha silyl carbanion. Okay, you generate a carbanion at this position. This can be done, for example, if you have SiMe3 R2 or Cl. So what you can do, I'm writing R dash. So what you can do, you can simply add a Grignard reagent here or alkyl lithium reagent. So what you need to generate is a lithiated species or carbanion at this position. So what it does, it attacks the aldehyde and it leads to the formation of this beta hydroxysilane. Now this beta hydroxysilane under acidic or basic condition, okay, it proceeds via different pathways of elimination which exclusively provides us E and Z alkenes. So this can be best understood with the help of examples, and in the examples I'll try to project how easy it is to predict the stereochemistry. Okay, so let us start the video with taking this particular example. Okay, first of all, I'm going to consider the elimination under basic condition. So as I said, under basic condition, the elimination takes place in a syn manner. Okay, let us take an example of this C3H7 SiMe3. This can also be written as TMS because this is nothing but trimethylsilane. Okay, so this is a single distereomer beta hydroxy. Okay, alpha beta hydroxy silanes. Now what happens if I use potassium hydride in THF? Then this being a strong base, what it does, it abstracts this proton and leads to the formation of negative charge species. SiMe3 O minus C3H7. Now what we want now is to bring these two groups in the same plane so that the elimination takes place in the syn manner. Now to understand this, we can simply convert this into a Schauer's conformation. Okay, and from Schauer's conformation we easily understand that this can be written like this. Okay, so if I try and write it like Schauer's conformation, just convert it into a Schauer's conformation, it will make our job much more easier, and understanding the mechanism and predicting it while solving a question much more easier. Okay, so let's just convert it. So since we can see this is C3H7, and since this is beta, so it will be on the right hand side. SiMe3, this will be on the backhand side, and since this is in the plane, that is why I have written it like that. Okay, and since this is O minus, this is beta, so it will be here. Okay, now what do we want? We want to bring these two groups in the same plane. Okay, let's just bring it to the axial position. Let's just rotate this bond. At the same time, rotate this bond as well. Okay, this can be written like that. Okay, SiMe3. So once SiMe3 moves here, C3H7 will come here, hydrogen will come here. Similarly, if the oxygen O negative comes here, then this hydrogen will come here and C3H7 will come here. Now what do we need to do is to simply write it in the form of the wedge here. Since this is on the right hand side, so this can be written like that, C3H7. This is on the left hand side, so it can be written alpha phase. This is on the right hand side. So just a second. Just a second. Okay, since this is on the right hand side, it can be written like beta, and this is C3H7, and we have this SiMe3O negative. So this O negative attacks, it leads to the formation of this SiMe3 negative, and we know that the countercation is always K positive here. So you can write it that K positive here, and then what you have is C3H7, C3H7. Okay, here how it takes place, the elimination takes place just like in the case of Wittig Olefination. The driving force is the formation of a double bond, silicon oxygen double bond here. So we can see this C3H7, these two groups are trans to each other. So in the product, the olefin that will form will be trans in nature. Okay, so this is what you will end up getting, C3H7. So this is how, if you can simply convert this into a Shor's conformation, and here what we understand that there is the bond rotation around single bond, the carbon-carbon single bond takes place. This is just to understand, so that while while answering this question, you can easily understand it and don't feel trapped to whatever stereochemistry that is given over here. So what you end up getting is the trans product. This is exclusively trans product, and this is how you have to approach this question. Now let us look at, had we used acidic condition, then what would have been the outcome. Let us look at that. I am going to rub it. Now the same diastereomer, okay, same diastereomer, but the only difference is now we are going to use the acidic condition here. Okay, so what we are using H2SO4, or we could have used BF3 threat, or we could have used PTSA. Here what we have is OH. Since we are using acidic condition, this is what it is going to form, C3H7. So in the previous case, the mode of addition was syn. That is why both these groups came to the same time. And here under acidic condition, both the mode of elimination is anti. Okay, this is something that we have to remember, anti-elimination. Okay, so now let's just write it, and absolutely the same thing that we have to do, which we did previously, to bring these two groups in the same plane. Just a second, OH2 plus C3H7. Now what we want to bring these two groups anti to each other and in the same plane. Okay, can we do that? Just try and write it in the same way which we did previously. So this can be written like that, SiMe3 hydrogen C3H7, and on the back side what we have is C3H7 OH2 plus hydrogen. So what we want now is to bring this to anti to each other. Let's rotate this bond here. Okay, so once we rotate, the silyl will come down, and what hydrogen is going to be here, and then C3H7 is going to be here. Similarly, rotate this bond. So I'm showing it in one go, but you can show it in in two-step sequence. It is just to understand. Now we are bringing this OH group on the top, OH2 positive, and if we do that, if this comes down, then the hydrogen will be here and C3H7 will be here. Okay, so now these two are anti. So if we can just simply convert this into the same plane, just do that. OH2 positive, SiMe3 positive. So this is on the right hand side, so this will be hydrogen and this will be C3H7. This will be on this side, so this will be hydrogen C3H7. Now what happens? Water it comes, it attacks the silane, this comes here and this goes. Again, since both these groups, they are on the same side, so the product here is cis. That is why you end up getting the cis product. Okay, C3H7. That is why you get the exclusive Z under using anti-elimination. Okay, so if you can simply convert this into Shaw's conformation and again into the Wedge-Dash conformation, then the prediction of stereochemistry is absolutely easy, and you can attempt these questions with 100% confidence rather than falling prey to a shortcut method. Now we are going to look at least 2 or 3 examples which are absolutely imperative from exams point of view. Let's look at those questions. Okay, so let's look at this question. So what we are given with this is this alkene having TMS group. So this, some in exam, just be aware, this could be written as TMS, so you should be aware of that. Okay, so what we are given is, we are given a complete sequence, and in the end the product is Z, and we are given certain step of sequence. Let us try and see. This is a very good examples of Peterson Olefination and very important example. So what we are given with is, in the first step, this ethyl lithium. Let us see what happens. So what can ethyl lithium do? So in this case, the ethyl lithium, it attacks this position. So what the intermediate that we end up getting is this. So we can write ethyl, it attacks here. So 2, 3. Okay, so this is what we have. This is what we end up getting in the first step, and in the second step it is attacking the, so we are given this propyl, and remember, so what do we have here? We have this alpha silyl group, alpha silyl carbanion, and we know when alpha silyl carbanions are either attacked with attacks aldehydes or ketone, they result in the formation of beta keto silanes. So this is exactly what happens. It will attack the aldehyde and it will lead to the formation of silane. Okay, so Me3Si, just let me write it a bit correctly. So this is a 1, 2, 3. So this can be written as propyl. Okay. So this is what we end up getting. Now, at this step, the role of this ammonium chloride, it is used to quench the reaction. That is the role of ammonium chloride. It's a very mild source, mild quenching reagent. So what you do is to make a solution of ammonium chloride and add into a reaction mixture, the reaction gets quenched. So here what we have formed is a alpha beta keto silane. Now what they have said, now they have used this is an oxidizing agent which is used to oxidize the olefin. Sorry, alcohol. This is Collins reagent. Si Me3 propyl, and in the next step what they have used is, they have used diol, which is used to reduce this OH group. Now one thing which we should be mindful of, since we are using diisobutyl aluminum hydride, the reduction of this can be governed by a Falcon-Ahern model. So this can be written like this. So if we write it like this, this is propyl group. Okay, and we know according to the Falcon-Ahern model, the largest priority group, this is the large group, it will be perpendicular to the carbonyl. This is 90 degrees, it should be perpendicular to it. And here on this side, since we have a hydrogen here, on this side one hydrogen should be here, and then an propyl group here. Okay, now since this is a diol is a reducing agent, okay, so this hydride, it will approach this carbonyl from the group which has the lowest priority. This is the smallest group, this has the lowest priority, that is why it approaches from this side. Okay, so what it does, it leads to the formation of this alcohol, hydride SiMe3 propyl. Okay, so if you can convert this into the solid wedge structure, so what you end up getting is this. Now what they have done in the last step? In the last step they have done H2SO4 THF, and we know whenever we are using acidic condition to this particular reagent, this particular reagent, then it takes place via under acidic condition. The elimination is always NT. So what we end up getting is the cis product. Okay, so that is how you have to approach this problem, and this was the Falcon-Ahern model. Falcon-Ahern model. Since we do not have any chelating group here, we do not have any chelating group. This is not a chelating group. That is why it follows the Falcon-Ahern model. Had we got a group like OMe, NH2, or some other group which can chelate with the aluminum that is present in the diball, then we would have got the different product. But in this case, it is governed by the Falcon-Ahern model. So that is how you have to do this question, and this is a very, very important question. Let us look at one more question. So this is another problem. So what we are given with this alpha chlorosilane, which is treated with magnesium followed by treated with copper bromide and then acyl chloride, and then the compound which is formed is treated with methyl lithium, which results in the formation of a compound which under basic condition gives E as a major compound, under acidic condition gives Z as the major compound. Now let's try and look what is happening. Okay, so let's just start with C5H11 SiMe2PH Cl. Okay, so in the first step we know magnesium and ether, what must be happening? It is leading to the formation of Grignard reagent. So C5H11. Now we know that, okay, and so let's just see this thing. This is already a carbanion, right? So now the question is why we are treating with copper bromide. It's an interesting question. For what we are doing, we are converting this into an organocuprate compound, because organocuprate compounds are much milder as compared to Grignard. Had we simply used this reagent to attack the acid chloride, okay, what we have end up getting is the tertiary alcohol. This is not what we end up getting in this particular reaction. Okay, so let us see what we get is SiMe3PH. So what we end up getting is this type of organocuprate compound. So mix organocuprate compound. Now when you add C4H9COCl, so this selectively attacks the carbonyl and it leads to the formation of C5H11 SiMe2PH C4H9. So this is the carbonyl compound that is formed. Had we not used copper bromide, what would have happened? This would have attacked the acid chloride and leads to the formation of a tertiary alcohol here, which is what we don't want. That is why in order to make it much milder, much more selective, so in order to make it a softer nucleophile, we have used copper bromide. That is the strategy we used. That is why organocuprates undergo 1:2 conjugate addition when we treat it with, whenever we are using cyclohexanone, organocuprate always undergo 1:4 addition, whereas Grignard reagent, they always undergo 1:2 addition, RMGX, whereas this is R2CuLi. Okay, organocuprate also 1:4, this is 1:2 addition. This is the reason why. Okay, so now this is, now what we did, this is then subject to treatment with methyl lithium. This is the same chemistry which we discussed previously. So what is happening? This methyl lithium is attacking the ketone. Again, this is also governed by the Falcon-Ahern model. So we can simply write it like that. C4H9. Again, larger group is this one. SiMe2PH C5H11H. So the approach of methyl would be from this side. Okay. and the product that I'm going to simply write, what we end up getting is C5H11. So this is something that you can do. Okay, and OH, here what we have is this methyl and C4H9. Okay, now whenever you treat this with basic condition, what we end up getting is the E as a major product. So you can simply write the mechanism of this one and get the desired product. The mechanism I have already explained how you have to go about the mechanism or carrying out this particular reaction. So that is how you have to approach such questions, and this is a very interesting question and a very high probability of being asked in GATE exam. Okay, so now let's look at one or two problems more. So here we are given with two more problems which are absolutely imperative and vital. So here what we have is this TMS alkyne, which is first treated with the borane species. So we know that the addition of borane onto the alkyne takes place in the syn manner. Okay, so whatever alkene that we get as a result of this is going to be the cis. This is something that we already know. So this is what we end up getting, propyl and TMS. Okay, because this is an organoboration, addition is syn. Now what we are doing is addition of MCPBA, metachloroperbenzoic acid, which takes place from the upper phase. So this is what we end up getting. So these are on the same side. They will be like, this can be written like that, propyl and TMS. Okay, now what we are doing, we are adding this organocuprate compound. Okay, so now as I said that organocuprate compound regioselectively it attacks from this type to give one only single regioisomer. So what it does, it attacks from this side, and the reason being this problem is very important because here we have there is a regioselectivity issues that is there. So it selectively attacks on this side. Okay, so now so what you end up getting if it attacks here is this propyl, just you need to write this TMS, hydrogen, propyl group, and this O negative, propyl, hydrogen. So what we are using here is this. Now this compound is subjected to potassium hydride. So we know that under potassium hydride the elimination is syn. It means this O negative and TMS group, they have to be in the same plane, but right now this is behind the plane. So what I need to do is to rotate this bond. Okay, and what I do if I rotate this particular bond, right now this TMS is behind the plane. If I will just simply bring it from back to the forward, then it means the propyl group is going to go in the back side. I hope you understand this. So this is TMS. Since what I have done, this is on the back end side, I have just pulled it forward. So this one was in the plane, so this has gone onto the back side. Okay, so this is now back side is the propyl group. Okay, so this is this hydrogen, propyl, and since this form this, elimination is anti. So the product that we, since they are on the same side, the product that we get is the cis alkene. Okay, so this is the product that we get here. So this is cis alkene Z. So that is how you have to approach this problem, and this is a very important problem. Similarly, what we are doing here, we are carrying out a dihydroxylation of this alkene using osmium tetroxide, and here what we have used, this is the NMO, which is a co-oxidant. What it does is this is used in the catalytic quantity, so this generates the osmium tetroxide in the reaction media. This is called N-methyl morpholine oxide. Okay, so what the now the dihydroxylation of this alkene will take place from the alpha phase, because what we have the bulky groups on the beta side. So this will be the product OAC, CO2Me, SiMe3. Okay, so this is from the alpha phase. Now what we are doing, we are treating this alpha beta hydroxysilane, so elimination. So the product is going to be this. So again, this is a very, very interesting and important problem from NET or GATE exams point of view. Okay, So in this video, what we have seen is the beauty of Peterson Olefination, wherein by changing the appropriate reaction condition, the elimination can follow either the syn or the mode anti mode of elimination to give us the desired E or Z olefin. Okay, so I wish I hope that you were able to understand this chemistry pretty well. In case you have confusion, you can just send me your comments, suggestions through emails or in the comment section. Thanks a lot for watching the video. Have a nice day.